In this video, we're going to be graphing a system of linear inequalities. So that means we're going to have two different inequalities. They may be linear, they may be not, it all depends. And we are going to graph them simultaneously. The answer to these systems is going to be the overlap of the two regional answers. So you're going to have the region of your first inequality, you're going to have the region for your second inequality. The overlap is the answer. If there is no overlap, then you have no solution. All right, so let's get to our first example. All right, so we have two linear inequalities here. I'm going to do the first one in purple, so let's start there. I'm going to graph that using intercepts. It's going to be dotted because it is strictly less than, so the line itself will not be included in the answer. If I put in 0 for x, I get a y-intercept of -2, and if I put in 0 for y, I get an x-intercept of 6. So -2 goes here, 1, 2, 3, 4, 5, 6 goes here, and then I would draw the dotted line through those. All right, and then I'm going to use my test. My test is going to be 0, 0, because I love to use the origin if I can. So is 0 minus 0 less than 6? And it is. So that means everything in that region, and I'm going to use purple for my region, this will all be included. So this whole area here will be shaded in for that inequality. All right, so we are halfway done. Now we need to graph the second inequality, again, on that same plane. So this time it has a less than or equal to, so it's a solid. Again, I'm going to use my intercepts to graph. So if I put in a 0 for x, I get a y-intercept of -2. And if I put in a 0 for y, I get an x-intercept of -3. So -3x is there, -2 is right here. I will draw the solid line between those two. All right, I'm going to test. Again, I'm going to test my origin because it's not in that line. So let's test 0, 0. And I get 0 plus 0 is less than or equal to -6. Well, 0 is not less than -6, is it not? So we are not going to shade above that green line. We will need to shade below it, and I'm going to shade that in green. So shading below it would be this whole area here. So your solution is right here. This is your solution. That wedge right there, where you have the overlap of the purple and the green highlighting, any point in that region will satisfy both of your equations at the same time. Both of your inequalities at the same time, pardon. All right, same example. This time, both of our linear inequalities are in slope-intercept form, so that will be quite easy to graph. The first one, notice this will be dotted. I'm going to do this one in green. We have an intercept of 4 and a slope of +2, which means if I go backwards, I go down 2 and back 1, down 2 and back 1. So a solid line right here. I'm going to test 0, 0 like I always have. So 0 greater than 0 plus 4. Is 0 greater than 4? It is not. So I would not be shading below that dotted green line. I would be shading above it. So I'm going to shade everything above. All right. Now let's do this second linear inequality is also going to have a dotted line because there is no equal to. It's going to have an intercept of -2 and a slope of 2. So up 2 over 1, up 2 over 1. So I will draw the dotted line there. All right, I will also use 0, 0 as my test. So 0 less than 0 minus 2. Is 0 less than -2? It is not. So I would shade the opposite direction. So I wouldn't shade above it, I would shade below it. So notice in this example that our shading has no overlap, right? There is no overlap. So the solution for this system would be no solution. Or if you want to use your null set, you can use that as well. So because there's no overlap, there is no solution for that. There is no point that will satisfy both of those inequalities at the same time. All right, another example. The first one, I'm going to rewrite that just because I don't like it when the y is on the other side. So y is greater than 2x. That is also in slope-intercept form. It has an intercept of 0 and a slope of 2. And notice because there is a strictly greater than, that will be a solid line. I mean, it's not solid, that'll be dotted. Dotted. There we go. So I'm going to draw my dotted line through that. This time I can't use 0, 0 as my test point because 0, 0 is on that line. So I'm going to choose a point over here. I'm going to choose this point, -1. So I'm going to test -1, 1. Every once in a while, it does go through 0, 0, and you're kind of stuck. So that's okay. We're just going to make the best of it. Okay, so let's test that. So y is 1. Is that greater than 2 times -1? And it is, right? 1 is greater than -2. So I'm going to shade above, and again, I'm going to do that in green so that it matches. So we're going to shade in green, and we're going to shade above this line. Which kind of makes sense for shading above because y is greater than, so above the line. So if you think about it that way, it works. All right, the second one I'm going to do in purple. That is also going to be dotted. And I am going to use intercepts for this one. So if I put in x equals 0, I get a y-intercept of 5. If I put in 0 for y, I get an x-intercept of 1. So y is 5 would be up here. And x1 is right here. I'm going to draw a dotted line through those. Notice this time that it is not on 0, 0, so I'm going to test my 0, 0 this time. So 0 plus 0, is that greater than 5? It is not. So I would not shade below this purple line, I would shade above it. Or to the right, depending on how you want to look at it. So we do have some overlap this time, that's good. So our solution is this little wedge right here. Any point in that wedge will be a solution to both of the inequalities. All right, this time we have a linear and a nonlinear, so this is nice. So let's do the nonlinear one in purple. That is a parabola that has been moved down 4 points. So our standard parabola, which everyone should hopefully know, it's going to be solid line as well. Let me put that on here. Over 1, up 1, over 2, 2 squared is up 4. So we would do that first, and then we would move the whole thing down 4. So let me erase those points. I'm going to put them down 4. So 1, 2, 3, 4. So here, over 1, up 1, from that point, over 2, up 4. Over 3, up 9, so 4, 5, 6, 8, 9. So here and here. All right, and that is going to be solid. So I'm going to draw in my solid. All right, then the question is, do we shade inside the parabola or outside the parabola? Again, I'm going to test 0, 0. I'm a big fan of 0, 0. So 0, is that greater than or equal to 0 squared minus 4? Is 0 greater than or equal to -4? It is. So we are going to shade inside the parabola. Oops, that was supposed to be my highlighter. Let's try that again. There we go. So I'm going to shade everything inside this parabola. All right, in green, let's do that linear one. This one is also going to be solid because it does have the equal to. I'm going to use intercepts. So if I plug in 0, I get y is 2, and if I plug in 0 for y, I get x is 2. So 2, 2. Whoops. So 1, 2, and 1, 2. And then I'm going to draw a solid line through those as well. And then notice 0, 0 is not on that line, so I'm going to use 0, 0 as my test to see if I shade below that line or above. So 0 plus 0 is less than or equal to 2. It is. So I'm going to go to my green highlighter, and I'm going to highlight everything below. All right, so the solution is this weird looking thing on the inside right here. So why don't I see if I can make that brighter or do it in red or something. I'm going to do it in red. That'll make it really stand out. So there is my solution. Anything in this wedged shape thing right here. So anything here that is my solution. So let me just label that. That's my solution. It's that weird looking wedgy thing right there in the middle. That any point within that section will satisfy both of these inequalities, both the linear and the nonlinear. All right, here we have another system. One is not linear and one is linear. So the purple one I'm going to do as my nonlinear. So that is a parabola that has been moved up 3 points. So normally it would start at 0, 0, but it's going to start at 0, 3. And then I'm going to go over 1 and up 1 each way and over 2 and up 4 each way. All right, and then that will be a solid because there is an equal. And then the question is outside or inside. Again, I'm going to test my origin because that is not on that. So I'm going to test 0, 0. So 0 is greater than or equal to 0 squared plus 3. Is 0 greater than or equal to 3? It is not. So I am not going to shade outside the parabola. I'm going to shade inside. So let's do that in purple. So these are all of the solutions for that first inequality. All right, now let's do this second one. I'm going to do that second one in green. All right, that is a line. It's going to be dotted this time. And because it's a line, I'm going to use my intercepts. So if I plug in 0 for x, I get a y-intercept of -1. And if I put in a 0 for y, I get an x-intercept of +1. So +1 and -1. And then that line's going to be dotted. All right, notice 0, 0 is not on that line, so that's good. So I get to keep my test point of 0, 0. So is 0 minus 0 greater than 1? It is not. 0 is not greater than 1. So I'm not shading above that line. I'm going to shade below. So let me switch to my green highlighter. And I'm going to shade everything below. And notice I'm not going to have any overlap, right? So this one will also have no solution. Again, in words, or if you want to use the symbol, the null set, that is fine as well. Again, no solution because there is no overlapping area. All right, so you may be asking yourself, what am I going to use this in real life? But that's always the question my students ask. There is a thing in business called optimization problems. It's where you have all these constraints and you need to know what I can do with all these constraints. So that's what this problem is about. So this problem is about Nikki, and Nikki has 2 part-time jobs. She has job 1 and she has job 2. And she has to make sure that everything is just right with both of these jobs. So let's find out all the constraints, and we're going to write all those down. So it says she never wants to work more than a total of 12 hours a week. So I'm going to call job 1 X, and I'm going to call job 2 Y. So if I add up the hours from job X plus the hours from job Y, that can never be more than 12 hours. It can be equal to 12 hours, but not any more than that. So those two have to be less than or equal to 12 hours. So that's that first sentence. All right, let's go to the next sentence. She has determined that for every hour she works at job 1, X, she needs 2 hours of prep time. And then for every hour she works at job 2, she needs 1 hour of preparation time. So 2 hours times X, because she needs 2 hours for jobs X, plus 1 hour for Y. All right, and it says that she can not spend more than 16 hours in preparation. So those two together have to be less than or equal to 16 hours for prep. So that is that second equation. So notice it's just a matter of me taking the words and turning it into math. So that was the second inequality we got from there. Okay, now it starts talking about money. All right, this is good. If Nikki makes $40 an hour at job 1 and $30 an hour at job 2, how many hours can she work per week at each job to maximize her income? Okay, so we want to, this is the whole gist of the matter right here. We want to maximize So maximize her income. What is her income? Her income is $40 times however many hours she works at job 1, plus $30 times however many she wants to work. So that's what we're trying to get to. We have a couple of inequalities that aren't in the words, but they're common sense. Like we all know that we can't work a negative number of hours. So we know that the X hours has to be greater than or equal to 0, and Y has to be greater than or equal to 0. We could work no hours at one of the jobs. That'd be fine. The only constraint was that we had to work less than 12 hours for the two together. All right, so all of these together, all of these constraints that we just had, see, these are all of our constraints. These are our constraints. We're going to graph all these constraints. And when we graph them all together, that should help us maximize her income. Now we're going to have to do a step after we graph. So let's graph all of these inequalities. So because we have both jobs has to be greater than or equal to 0, I just have a graph of the first quadrant because I knew that's all we needed. We're talking about time. Time can't be negative. So I know that everything's going to be positive and positive. So that's why I only use the first one. All right, then I need to graph these two, the one in the green and the one in the red. So let's start with the one in the green. So that's X plus Y has to be less than or equal to 12. So that would be 12 here. And that would also be 12 over here, but notice we're not gonna, that has a slope of 1. So I'm just gonna put a dot for each one. So I can keep my line nice and straight because my y-axis didn't go all the way up. My x-axis didn't go all the way up to 12. And that's a solid line. All right, so that's that constraint. And it's less than or equal to. Again, if you use your test point 0, 0, you would find that that would mean we would be shading underneath. So I'm going to shade everything. Whoops, that is not my highlighter. I thought I clicked my highlighter. There we go. So we're going to shade everything under here. All right, so everything in this triangle. Let's see if I can get that a little nicer. Oh, there we go. That's better. All right, so everything under here satisfies, everything in this triangle satisfies the first constraint. All right, now we're going to do the red. All right, so if I use my intercepts for that, I would have an x-intercept of 8, and I have a y-intercept of 16, which obviously isn't on the graph. So you'd have to use your slope. If you change this to slope-intercept form, you'd have a slope of 2. So let's see. Dun, dun. Oh, look, they meet right at that point. Okay, both of the graphs meet at that point right there. That's lovely. Okay, and them meeting at that point is really important. That point right there is 4, 8. So I'm going to label that because that's kind of important. And then we would go also underneath that graph as well. I'm going to do that in yellow just to make it. So everything under here. So notice the area that I'm really going to focus on, I'm going to do this in red, is the area of overlap, which is this section right here. So somewhere in that section is my maximizing income. So the important thing that you need to know when you're maximizing income, X, Y, and I. Okay, is you're going to look at what we call critical points. And the critical points are the boundaries. So somewhere on the boundary of this thing is my answer. So I've got a couple of boundary points. I've got the origin, 0, 0. I've got the point right here, 8, 0. I've got the point 4, 8 that I found. And I've got the point up here, 0, 12. So those are all the boundary points on that weird looking thing. So that is those are our boundary points. And if I plug in each of those boundary points into my income, that will, I just need to look for the biggest one. So here we go. If I work 0 at either job, so 0 times 40 plus 30 times 0 is going to give me no money. That's definitely not that's not my maximization point. That's my minimization point. I don't want that. Okay, let's try 8, 0. If I plug in 8 times 40, that's 320 plus 0 times 30, that's 0. So that's 320. All right, then let's do 4, 8. 4 times 40 plus 8 times 30, that would give me 400. So that's better. So 8, 0 is out, right? This is out. This is out. So far, this is the winner. Now let's try 0, 12. 0 times 40 is 0. 12 times 30 is 320 as well. No, 360. So that one's out as well. So it looks like our maximization point is right here. So the point that is going to give her the most money is she wants to work 4 hours at job 1 and 8 hours at job number 2. That will give her the most income that she can get, which is $400. And again, these are called maximization problems. In business, it's called linear programming. So that's another thing that you might see it listed under something called linear programming. So another place that you might see graphing these inequalities. So hope you enjoyed, and I will see you next time.